So welcome back again to the demo class. Okay, so we have seen that means the example with adder, that is a purely combinatorial block. So how to, that means set this don't touch network, and then that means how to, that means stop the optimization process. That means first we have seen how the design compiler itself that we optimize the circuit. Then we have seen okay how we can stop the optimization by setting the don't touch network. Okay, then now we will see one purely that means sequential circuit element, which is nothing but any resistor like D flip flop or something else. Okay, so we will see with that basic example in the next. So again, to start with, what I have to do, I have to write the code for a sequential element, which is a D flip flop. We will take an example of D flip flop. So to start with that, again you go to this gedit, then write module D flip flop. Okay, then the module, that means input are clock, reset and Q. Q is the output, and the input is clock and reset, and the output is Q. Then so after that, as this is a sequential element, I'll that means by its but that means I'll write the code in the behavioral level. So within always block, whatever is there in the way according to the Verilog syntax, we have to mention that as reg. Okay, so I am mentioning that Q as the reg, then always at the rate of positive edge of clock, if it founds reset equals to 1, then Q will be 0. Q will be 0. Else Q will be there will be another in the D flip flop, there will be the input which is D, that I have mentioned, forgot to mention. So and then okay, so this is it. So this is the code for the D flip flop, which is a purely sequential element. So save as, right, then save it. So then again this, okay, I have to open up this design vision environment, and in this design vision environment again I have to set up the library, as I have closed this. So I have closed this to show you that okay, if you close this, then again this will be just reset. Okay, so I have to do that thing again. That means I have to set this library name. So here these things, this typical, and then for this also the same thing, same, that means what is link library, that is my target library. So I'll select that thing here, and then for this symbol library I have to add this digital standard library, synopsis, models, this lib. Okay, so once this setup has been done, now I will read the D flip flop Verilog file. So you just okay, so I have made some mistakes. So that means whenever I am reading, so at that time it is checking the syntax. So I have made something mistake at the line 15. Okay, so line 15. Oh, this is and module, right? So save this, then again reread this one, and okay, done. So that means whenever I am reading, it is checking the Verilog syntax. If it is found that okay, anything is wrong, so it will show you the error as it is already shown to me. So after that, again you have to do the same things, analyze and elaborate. So analyze this thing, this D flip-flop, okay, to the work, and then elaborate it, D flip-flop. So here actually in the combinatorial circuit we don't have any clock. So that's why we have not set the values for clock. But here I am having the clock, as this is purely synchronous, that means sequential circuit. So now we have to set the period for clock. So to set the clock, you select the clock, go to the attributes, click on the specify clock. So clock name anything you can give as clock 1, clock 2, clock 3. So I will give the same name as clock what I mentioned in the design. So period is, let's say that is 2 nanosecond is the period. So it will be started at 1 and falling at 1, sorry, started at 0 falling at 1. Okay, so this is the things. So here the clock you can select this. If you select this don't touch network, that means at that time, so during optimization or during the compile process, this clock network will not be touched. Okay, so for single D flip-flop I am not considering this set don't touch. And another option is also there, fix hold. If any hold violation is arrived on your clock network, so if you click on this or if you check this box that fix hold, so during the compilation automatically it will try to fix those hold violation by putting some extra buffers or any other techniques, right? So then what I have to do, then okay, once I have set the corresponding clock, then what I have to do, I have to, this reset is my input. So for reset I have to set the corresponding, that means delay for it. So delay here I can set that as 0.1 and here 0.1. That means the rise time and fall time for delay, that is 0.1 with respect to clock. And here you see that whenever I have, in the earlier case whenever I was trying to do, at that time it was show me warning that okay, no clock is available, but as this, for this design clock is available, so that's why I can easily select this 0.1 as the rise or 0.1 as the false for reset. Okay, so this command is already there in the command prompt. So after that, again what I have to do, you can select, you can just click on this, then select the corresponding this well load model, then this that is the operating condition. Now I am setting the well load. So after that again I can set that okay, the design constant as 0, and for timing again with respect to clock or with respect to something I can set, but I will not set the values here. So the area values, that means area constant values I have set, the timing constant values also I have set. And now what I will do, I will just go to the compile design and I will compile with the map effort of medium. So while I have done that, so at that time you see that so this is the corresponding schematic of that. So as actually as I have put that okay, there is a condition for reset, that if reset is 1, then it will be that means 0. If reset is 0, sorry, if reset is 1, then at that time it is 0. If reset is 0, so at that time it is 1. So that's why this D or and reset, that is basically passes through this logic to the input of this Q range, right. Now this is the that means the implementation of D flip flop. Okay. Now after that, what I have to see, in the earlier case, whenever I was trying to check the timing, so at that time I was unable to do that. But in this case, if I just click on this, that load the timing analyzer, so at that time it will show me these things. Okay, that what is the arrival time and what is the required time for that. So the actual arrival time is 1.22, though the required time what I set based on that 2 nanosecond particular clock and then rise time of 0.11, sorry 0.1. So the required time is 1.96, but actual arrival time is 1.22. Okay. So what is the slack? Slack means the basically the definition of slack is the required time minus the arrival time. Okay. So if the required time is more than the arrival time, at the time it's okay. But if the arrival time is more than the required time, so at that time you will get negative slack. Okay. So negative slack is not at all practicable. That means for practical solution, negative slack will be avoided. You need the slack that should be near to 0, is 0 or nearer to be 0, not in the negative, that will be in the positive domain. So what is that means slack? If I just click on this, what is the path slack? So it will show me the corresponding path slack. So the best that means what is the slack? That is the slack value is 0.742778. That means again what I can do, that means the clock period what I said, that is 2 nanosecond, that is more than, that means again I can reduce the clock period by let's consider 0.8, again I can reduce. So if I reduce that thing, again what for that reason what I have to do, again I have to go to the specify clock, and this clock that I have to set as, initially I have set that as 1.2, now 0.8 surplus I am getting on the clock, so I will set that as a 1.2, and then that is 0.6. Okay, so now again click on that. After just setting the corresponding clock, now I will do what? I will compile the design. So now after that again I will check, okay, whether that is meeting, that slack is meeting or not. So if I see that, okay, so the required is 1.16, but the arrival is 1.22. So if you just click on this check timing, so it shows that, okay, slack is violated, that is by minus 0.06. That means 1.2 that cannot be set. So 1.22 is the value for which the clock will be, the clock period will be the optimized one. Now for that reason, so if I set not 1.22, actually that will be 1.26 basically, because for rise time, fall time I need the extra values. So if I set the clock as 1.26 with this 0 and this with 0.63. Okay, so after that again you compile. So now you check the timing. So here you see the slack is 0 and it is met. So that means the minimum period for the D flip flop what I designed, that is 1.26. So 1.26 means the frequency of that designed flip flop that will be near about like 1000 divided by 1.26 megahertz. Okay. So in this way we basically design in a design compiler. So this is just the basic to show you that how the basic elements, how to start with. I have started with the basic elements adder for a combinatorial circuit, and that means D flip flop as for the that means for the sequential circuit. Now what I will do in the next example, I will take I will design one 16-bit counter, and I will again in the 16-bit counter what I need the that means sum of the part sequential and sum of the part combinatorial. So both the parts are there in a that means 16-bit counter. So I'll just code that, and then again I'll compile all these things to do that means how it is basically working. So for that reason I'll just remove this design from this. Again what I have to do for that, I have to that means I have to write the code for it. Okay. So now the module name will be count 16, then clock reset, and count is the output, then input name is clock and reset, the output is 15:0. So this is raised, positive is sensitive that counter I am designing. (16.D0) else count equals to count plus so that means here this logic is that means always at the rate positive edge of the clock, if reset is found that was 1, then it will be 0, else if it is not reset is not 1, then it will be counted at the each of the edge, that means for positive edge it will count up by 1. Okay. So now this I have to save this as okay. So now what I will do, I will just again read these counter values, these counter files here. Okay, so something is line 14, where is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, again I have written this wrongly. So this is this I have read, that means I have read this counter file. Then I have to do what? I have to analyze this counter. Okay, then after that what I have to do? I have to elaborate. So here the top module name will be what? Counter, not the D flip flop, right? So this is the counter. So top module name is counter. So that I have done. So after that again the clock will be again it will be constraint. So here I don't know what will be the corresponding that means delay for the clock. So here in the last the example what we have seen, that 1.26 was the delay for that means 1D flip flop. So we are taking that 1.26 as the starting point of ours. Okay, so 1.26 is the period what I said, and that is 0.63 is the this one. Okay, and after that what I have to set, that means I have to set the corresponding values of this, that means what will be the rise and fall. So this is 0.1 and this is 0.1, right. So after that this the whole module I have to set the operating condition, I have to set the valid model, and I have to set the corresponding a maximum area, that is 0. Okay. So once I did this, this is the basic constant which I only put, because here I don't have the list of the specification for this particular design. This is just for the starting with, that means how you can start with this. So whenever you will work on this environment, so at that time, that means suppose you have some projects to do or you have some work to do, so at that time you will have that concrete list of specification in your hand. So based on that particular specification, now you will get the corresponding, that means constant. So that constant now you put in the DC environment and you compile, start compile. So after that what I will do, I will start with this compile design. Okay, so once I start with this compile design, so at that time it will be started compiling. Okay, so after compiling, you see actually it is passes 2-3 actually phases of optimization. This is phase 1, this is mapping optimization, then beginning area recovery phase. Okay, that okay, then after that they are beginning delay optimization phase, where this that means area has been increased. Then it is starting with area recovery phase with, as I said, that okay, maximum area is 0. So again it is basically reducing the that means area. So initially what it started in the mapping optimization phase, it is started with 999.9, that means 1000 almost, and then in the delay optimization phase it is 993, and in the area optimization phase that has become 927.6, right. So that means this is the last things it can do for this particular specification or this particular constant what I put to the tool. So and this that means what are the job of this, that how the optimization flow occurs, that I have already mentioned in my presentation, that okay, this is the steps which it follows. It starts with mapping optimization, then this delay optimization, then area recovery finally, and then compilation done. Okay, so the same thing you can see, or you can just correlate with the presentation as well as this tool demo. So after that what I have to do, after that again you can go to the design, then you can check what is the area for this. So here you see the combination, whenever you are that means checking the area requirement. So at the time, as this counter has two parts, what I said, combinatorial part as well as the sequential part. So here it is showing that okay, how many ports you are using, total number of 18. So how many nets, total 51. How many cells, 34. Among them, how many combinational cells, 17, and how many sequential cells, 16. So total combinational cell area is 495.8. Then for inverter or buffer, that is 38.7, and for this macro blocks, as I have not put any macro blocks, so that is for 0. Then for interconnect area, that is 33.6. So total cell area is like that means 927.6. So cell area is 893.9. Along with that, so total area is net area plus the cell area, that is 927.6. Okay. So now next what I will check, I will check the what is the power, what is the power consumption for this. Just rough estimation of the power consumption. actual power consumption you can get only after providing the switching information file to the that means then only you will get dynamic power consumption very accurately. But here you will get based on that frequency how basically that means that's just the rough estimation of this leakage power optimization as well as the this dynamic power that means consumption. So here you see that internal power is this, switching power is this, leakage power is this, and the total power is 33.3363 that means microwatt. But this is not the actual case. That means this is not the actual power consumption which you will get in design compiler. This is the rough estimation of that means to visualize that what is going to happen on the power consumption side. So after that what I will check, what I left, that is timing information. So timing analysis driver, if you just click on, so here you will get that okay, there are several paths from input to the outputs, right. So there is through from clock to the Q, that means 16 outputs are there. So 16 from clock 2, so that's range 1, then range 2, then range 4, 3, 5, 6, 7, 8, 9. So total 16 paths will be there, and then from reset to another path. So from here actually what I said that okay, the required time is this one, but the arrival time is very much less here. So arrival time is here, for here that is 1.16 for the range 13 only, and if I want to see that which path is basically is, so you just click on this, so it will show you that which path is basically taking that time. So that means this one is the, that means this clock to range 13 is taking the maximum one, and range 15 is taking the maximum one, that is 1.16. So if you just click on this schematic view, okay, so you have to go back. So here you see this is the path it is basically highlighting. Okay, so this is the path it is highlighting, that this is range 0, this is range 2, this is okay, this is range 14, range 13, something like this. So this is the adder for counting up from that, from clock 2, this is the range 15, from that how it is going. And why this range 15 and range basically 14 is this that what is that range 13, 14 and 15, they are taking the maximum value because I am incrementing by 1. So that logic has been added onto that particular that means okay, so that particular register it is being used on the LSB side. So that's why this is this has been added, or this is getting maximum number of arrival time here. But on the MSB side, as that is not at all related, or that is not at all connected with the logic itself, that means any logical gates, so that's why they are taking less amount of time, even that is 0.44. okay. So then again I have to check okay, that timing information, whether that is slack is meeting or not. So here you see that okay, the data arrival time is 0.44, but the slack is met and the timing is 0.76. So that means initially what we took that as 1.26, but here I can also reduce that as a reduce from 1.2 to more than by 0.7. okay. So again what I have to do, again I have to set, or I have to that means change the corresponding clock value. Now if I that means set these clock values to 0.7 means 0.5. So here okay, this is not by hand, this is 0.56, this is 0, this is 0.28. okay. So again if I just compile the design, so at that time, so here you see the area requirement has been increased a lot. So initially it was 927, now it has become 13.7, because there is a trade-off between area and timing. So while I am trying to, that means reduce the timing, so at that time obviously it will, the area on the area side it will be increased. So how it has been increased, that, and whether that timing has been met or not, you just check. So the actual data arrival time is 0.78, but I have said that as 0.5. So that means 0.8 will be my again, that means as this is getting negative, so again I have to change it. So I have to change it means, again I have to set that, okay, as this attributes, that as 0.8, then that is 0, then 0.4, and then compile design. Okay, then again check whether that is meeting or not. Okay, again that is by 0.04 it is not meeting, so that means that will be 0.84. so again you select that as that is clock 0.84 to 0, and that is 0.42. Then you click on this, then go to the timing, and so now it has been met, right? So it has been met means the 0.84 will be the optimized clock period for my counter 16, right? So what I did is, that means now for counter 16 that can run 1000 by 0.84 megahertz frequency. Okay, so power consumption for that, obviously that will be increased, as that means the rough estimation that will be increased as the frequency has already increased a lot, because earlier we have set that as 1.26, now we are setting that as 1.84. so obviously the power consumption will be also increased, and the area is also increased by a lot. Not lot, that means earlier it was for 927, now the area requirement became that is 1228. Okay, so the interconnect area also increased, and that means the number of nets increased. Earlier it was 51, now it became 61. The number of cells, that is also increased. The combinational cells also increased. Okay, so for that reason, this initially it was near about 500, now it became 779. So the combinatorial circuit has been increased, that means the fast adder, it has been incorporated to maintain the, that means the corresponding speed requirement. Okay, so area wise it has been increased, but delay wise it has been decreased. So there is a trade off between that. So in this way, so then till now what we have seen that, okay, GUI based, using the GUI we can do that. That means we don't have to put the command prompt, just by clicking on that we can easily do that. But for a bigger design, whenever I have to run that system for, let's say, 10 iteration or maybe 100 iterations, so at that time manually to do this every time, it is very much painful. So that's why what people do, they just, that means write the script for that, for each of this part. So in the script only they just change the value, and then go to the file and execute the script. So whenever if there is a script file is there for this, that means the same purpose. So if you run the script, that means if you just write the script file and you run the script file, these things can be done automatically one by one, and you will get the results. Okay, so that's why in industry basically people prefer to use the scripting language. Okay, so actually this prime time, whenever we will use prime time, the prime time there is no GUI, that means it has to start with the scripting language. All the things it that means takes the script as only the input. There is no such GUI or nothing else. So at that time we will use this script. So for this, for today, I think this is the beginning to start with, and what I have to do and what I left, actually this counter 16 module, we will take this netlist file for further of my design. Okay, that means for functional simulation, for that means physical design, for that means timing analysis, for power analysis, everywhere we will use, because this is that means a good example of, as it consists of that sequential element as well as the combinatorial element. So whenever we have synthesized it, we have got the optimized netlist. Okay, we know that okay, this is the optimized one, and there you see there are another options too. That means for testing, if you want to insert the scan chain, you can do using this, that means tab. If you want to check the corresponding power, you can do, and this analyze RTL format also you can do. That means whatever netlist file you have created, that the functionality of that is correct or not, that also you can do. So once you have done, or you have got the netlist file, optimized netlist file, then that you have to save for further use. So how you can save? You can just go to that save as option, then you write count optimize.v, and the format is Verilog, then save it. And another thing is that we have to write the corresponding design constraint file which we have used here in this to obtain the corresponding netlist file. So how to do that? You just write this comment, write _sdc, then with the name of count.sdc file. Okay, so these things we have done. So after that we will exit this. That means this is the end of the design compiler. This is not the end of the design compiler. There are so many things, other things are there which you can do, or you can explore in the design vision whenever you are working with the bigger net, that means bigger design. Okay, so that means for the basic things I am just cleared, and whatever comment I have shown in my presentation, that will be used for while I am using the bigger design, because that thing will be affecting the bigger design, not the smaller thing. So that's why you can just I'll provide some of the, that means Verilog files and this scripting language as a supplementary to this video. So at that time you can just go through that and you can check whether that is working fine, or whatever I have mentioned that is working fine or not. Okay, for today this is it. Thank you.